Hello friends, in today's question, a large open top container of negligible mass and uniform cross-sectional area A has a small hole of cross-sectional area A by 100 on its side wall near the bottom. The container is kept on the smooth horizontal floor and contains a liquid of density ρ and mass m0. Assuming that the liquid starts flowing out horizontally through the hole at t is equal to 0, calculate the acceleration of the container. And part B, velocity of efflux when 75% of the liquid has drained out. So this question, you can say, is a combination of, we can use here the properties of matter and based on some your Newton's law of motion also. So in this case, we are interested in finding out the acceleration of the container. So obviously, if there is acceleration, some kind of force will be also present, because of which this acceleration is going to take place, and we have to suppose to find out the acceleration of the container. So let us first of all start from there only, at the force and acceleration. So it is given in question that suppose this is a smooth floor and we have some kind of container and there is a side hole at near the bottom. So let us suppose the hole is somewhere here and the liquid start flowing horizontally in this direction. So because of this, there will be reactive force on the container, and because of this, the container will be trying to move in the opposite direction. So this is basically the force and acceleration. We are going to discuss the same thing with a liquid, and so we can say from here that the liquid flowing out of the hole exerts a reaction flow force on the container causing it to accelerate in the opposite direction. Causing it to accelerate in opposite direction. Or we can say that what is going to happen as the liquid will start to come out, the level of the liquid is going to start to decrease on the this container. Okay, so what is, we can make a conclusion from there that the force is going to arise from the momentum of the liquid jet. Okay, so we can make a conclusion that the force arises from the momentum of liquid jet. So let us first of all find out what will be the, you can say, velocity with which the liquid is going to exit the hole, and for that we are going to use Torricelli's theorem. So velocity of the liquid exiting the hole. So we can say by Torricelli's theorem velocity of liquid exiting the hole let us call that as V out, and it will be equal to 2g multiplied by h. And this velocity h, because h is the liquid column, suppose this is the height, and with the passage of time this height is going to reduce. As more and more liquid is going to flow from this hole, the height is going to reduce. So we can say this height is dependent upon the time. So we can replace this h by h of t, and we can say that this h of t is height of the liquid column at time t, at time t. So in this question everything will be time dependent, because with respect to time the level is going to reduce, and accordingly the momentum will be your, because momentum is our also a time dependent. That's the first derivative of. Therefore we can also find out that the volume of the liquid column, volume of liquid column at time t, let us call that Vt, and Vt will equal to mass with respect to time t divided by density of the liquid. Okay, and mass is given as m naught, so let us write this as m naught. So we can write this here as volume will be equal to height multiplied by the area. Okay, so we can say that our Vt will be equal to our Ht multiplied by area, which will be equal to our m naught t divided by rho. And from here we can find our height will be equal to m naught t divided by rho a. So from, if we substitute value of this height in the velocity equation, so we can write that our velocity will be equal to 2g, and we have m naught t divided by rho multiplied by a and its square root. Now we are going to find out what will be our force and acceleration of the container. Force and acceleration of container. So you can say rate of change of momentum of exiting liquid, the rate of change of momentum of exiting liquid is our force, let us call that reaction, will be equal to m first derivative out multiplied by v out, where this first derivative m out is our rate of change of mass flow out of the hole. This is our first derivative is our rate of mass flow out of the hole. and we can find out this our out first derivative will be equal to rho multiplied by its area of the hole and multiply with the velocity with which it is coming out, that is V out. And we already know the formula for V out, we just found it, substituted here, and or we can just substitute here. Let's find out first of all F reaction will be equal to, we have this rho A multiplied by 100 and we have V out and V out, so this will becomes as V out square. Now we can substitute the value, so this gives us rho A oblique 100 and this comes as 2g m naught t divided by rho A square root and whole square. Square cancel with this, so we are left with rho A 100 multiplied by 2g m naught t divided by rho A. Rho A cancel and 2 goes with this 50, so we get this as g m naught t divided by 50, and we found out the force. Now we can easily find out the acceleration, so we can say acceleration of container let us call that A of t will be equal to reaction force F reaction divided by mass of the container, because that will be fixed, plus m naught t mass of the water, which is time dependent because with the time this is going to change. And we can treat that the mass of container is, in the question it is given, is of negligible mass, so we can say mass of the container m container is approximately equal to 0. So we get our acceleration, it will be now equal to F reaction divided by m naught multiplied by t. We substitute the value g m naught t divided by 50 and whole divided by m naught t, and this mass goes with mass, so we get acceleration will be equal to g divided by 50. So this is the acceleration of the container, part A. This is the acceleration of container. And we come to part B. So part A is complete. Part B states that velocity of a flux when 75% of liquid has drained out. So in this case, we can directly use the velocity Torricelli's theorem once again. The only thing is that it is given that the 75% of liquid has drained out, so it means only 25% liquid is available inside the container. So little bit the formula is going to change, and we can use directly the Torricelli's equation. Okay. So we can say for part B, by Torricelli's theorem, let us call the velocity is given as v is equal to 2gh and it is square root, and in this case it is given that now only the 75% of the water has drained out, so it means 25% is only remaining. So the present height will be equal to 2g, 0.25 of h. And where h was our initial height in the container. Let me write it here that h was our initial height of liquid in the container. So we substitute the values, we get our V is equal to, we have here, yeah, we can also find out our, you can see H, and let me further solve it. And M naught was the initial mass, of liquid. So this initial mass of liquid, that is M naught, can be written as A multiplied by initial height multiplied by its density, and H we can write out further that it will be equal to M naught divided by A multiplied by rho. So we can substitute value of H. So we get that V is equal to 2g multiplied by 0.25 multiplied by M naught A multiplied by rho and its square root. So this comes equal to, as this will be our 0.5. 0.5 can be written as 1 by 2. So this becomes our G M naught divided by 2 rho A. Write it again. So velocity of the efflux when 75% of the liquid had drained out is given as G M naught 2 rho upon A. So you can say this is the velocity of efflux when 75% of liquid has drained out. Liquid has drained out. So this completes the question B part also. This completes the question both part A as well part B. Thank you.